Major support for Do the Math has been provided by CHEVRON, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary STROOPE Family Foundation, Panama-BUENA VISTA Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
And I'm Devin.
And in studio with us we have Matthew. And Matthew, if somebody needed to get a hold of us, what would they need to do?
For math homework help, call in Bakersfield 636-4357, toll free 1-866-636-6284. Our email is dothemath@kern.org. We're online at dothemathonline.net. And on social media, Facebook, Instagram, Twitter, and YouTube.
All right, nicely done. Thank you very much for that. Where do you go to school, and what grade are you in?
I go to Stockdale Elementary, and I am in 5th grade.
How long have you been at Stockdale? For a long time or recently new?
Since kindergarten.
All right, so you've been, this is your 6th year being there.
Yeah.
What do you look forward to most next year? Because next year will be your last year at Stockdale. You've been there for a long time. What are you most looking forward to next year as your 6th grade year?
Probably science.
Probably science?
Yeah.
All right, good. What kind of science do you do in 5th grade right now? Do you do a lot of science right now?
Mainly experiments, like little fun. They're pretty fun.
All right, good. So you get to do some things and learn by doing some different experiments and things like that?
Yes.
Good. How's math going so far?
Pretty good.
All right, good. Well, we're going to do a little bit today if that's all right with you.
Cool.
All right, good. Well, you know what? If any other students phone in today and they do a math problem, right?
Right.
They're going to get a ticket to Holiday Lights at COM.
Holiday Lights is back for its 18th year in a way to keep you safe and socially distant. This year, Holiday Lights at COM, presented by Dignity Health, lets you drive through millions of lights and colorful displays from the comfort of your car.
What? All you have to do is between this week and next week, Tuesdays and Wednesdays only, today the 1st and 2nd, next week the 8th and 9th, all you do is phone in to do the math. We do your math problem on air, and you've got yourself a Holiday Light voucher, and that's some of the attractions you'll be able to drive through. You can see right there, it is a little bit different than in years past where you would walk through everything, but you can see all of the lights that are out there, kind of how it's laid out a little bit.
This is one of the top 10 light shows in the country I saw come out from a survey that was just
Right.
released.
Now,
Yeah.
I think one of the favorite in Bakersfield every year, and actually I think, the Western United States, it's a pretty big deal. But if you and your family have a family tradition of going to Holiday Lights at COM and you haven't gone yet, you can go for free. All you have to do is give us a call today or tomorrow or next Tuesday, Wednesday. You get yourself a free voucher and save yourself a $30 ticket right there. It's not a bad deal, is it?
No.
All right. Well, you know what? We're going to do a little bit of math with you in just a few moments.
Okay.
But right now it's time for today's Math in the News. All right, in today's Math in the News, we are fortunate enough to have Isabella Caputo in studio with us. And Isabella, you are with the Ford Dimension, correct?
Yes.
All right, so first of all, explain what Ford Dimension is.
Yeah, Ford Dimension is a leadership program that focuses on helping seniors in high school gain necessary skills for the future, along with being more active in their community.
And what high school do you go to?
I go to Bakersfield High School.
All right. And you obviously are a senior this year.
Yes.
And how did you learn about the fourth dimension?
Yeah, so initially my counselor sent me a request in order to apply for this program, and from there you get to go through many different tributes of things, and this year it's obviously a little bit different. However, in normal years you would go to a welcome night where they kind of tell you a little bit more about the program, along with they also have an interview process, and it's very extensive on how you get in the program because it's picking the best of the best.
Right. And you learn about this during your junior season,
year.
right?
Yeah.
Okay, so during your junior year, you find out about fourth dimension. Now, when you were younger, when you first started high school, did you even think about this at all? Was it even on your radar? Did you know anybody that was in it, or you just didn't even think about it until they offered it to you in your junior year?
Yeah, I definitely had a lot of previous knowledge from it because my sister was in the program,
Okay.
and she's 4 years older than me, so I was kind of a little introduced into the program. However, I didn't want to follow in her shadow, so when the counselor sent me that request, I knew that it was my time.
Good. And that does happen a lot of times where somebody goes, well, you know, they did it. I don't want to do that. You
For
know,
sure.
especially if you're really close like that.
Yeah.
So how many kids are in fourth dimension?
Yeah, so there are 300 applicants throughout the program, and then from there it gets picked down to 32 people, and that is called your 4 Dream Builders. And then from there are 10 picked for the 4-dimension program, which are basically going to be the ones that are representing the 4-dimension program within the community.
Okay. And speaking of, now that's the whole reason there is a fourth dimension, is to help the students,
Yes.
but also to help the community. So what is the project that you're working on this year?
Yeah. So I'm a part of Team ERA, and our goal this year is to educate students, 3rd through 6th graders, about possible opportunities within the STEAM field. So we're going to be having a webinar night that goes through each of the fields, so science, technology, engineering, the arts, and math, and we'll be able to have inclusive video with different science experiments that the kids can get active into, and it's called Full Steam Ahead.
Okay. And what about your advisor? Like, how much input, do they kind of like guide you into a project, or do they say, listen, you're the kids in this, you come up with something and I'll help you? Or how does that work?
Yeah, so we actually have 6 advisors on our team this year, so we get a lot of help. However, the first initial project is your team coming and brainstorming everything. So I think we had about 10 initial things, and then after that, we wanted to get more information from our advisors, and they helped us dwindle it down, but in the end, it's the students helping the community.
Okay. And if there are some students in high school right now, or maybe even junior high or younger, and they're going, you know what, I've kind of heard about this a little bit, and it sounds something that I might want to get into as I become a junior or senior and stuff like that. Is there anything that a younger student could be doing to kind of groom themselves to be a part of this project later on?
Yeah, for sure. I would definitely check out the website, jimburkeeducationfoundation.org, and from there you can learn a little bit more about the program, but it's mainly you want to be active within your school. You want to show that you're a good student and you can keep up your grades while having fun and either being in student government, band, athletics. They really want the all-around best kids from your school.
Right, and I think that's the key, is the all-around student. Instead of just being, all right, well, I've got a 4.5 or whatever it is, and you're book smart, everything's great, but do you do anything else?
Exactly.
That's what they're looking for.
For sure.
And I know that your project is full steam ahead,
Yes.
and the S stands for?
Science.
There you go. Now, our young friend back here, Matthew, I believe you had a question for Isabella.
What are the science classes like?
They are amazing in high school. I know I was very blessed to have some very nice teachers, but I took honors biology and honors chemistry, along with right now I'm taking AP environmental science, which it's a little bit different in COVID. However, it's very active and you get to do projects and different things. I love it there.
I look forward to joining that.
For sure.
Yeah, so a lot of science. You'd be able to take 4 years of science
Yes.
when you're in high school instead of just doing the 1 or 2, whatever you need and stuff like that. Well, anyway, Isabella, we certainly do appreciate you coming out and telling us a little bit more about the fourth dimension. And also, thank you to, so here's a question I've got for you. Because there are a lot of adults that do the math. And I'm sure that a lot of them have heard about the fourth dimension. But the advisors are all adults, and some of them are actually former fourth dimension participants and dream builders themselves. Is there a way that an adult can help with fourth dimension, as far as you know. You may not know, but.
Yeah, if you check out the website, they can get more information on there. However, if you reach out to Katie Roldell, she can get you all the information to either get you plugged in a group of students, so then the adults can be one of those advisors, or anything like that.
All right. Well, thank you once again, and thank you also to Katie for getting in contact with you to allow you to come on and do the math. We certainly do appreciate it. And that is today's Math in the News. 636-4357 is that phone number. We do have phone tutors available until 5:30 this afternoon. And as a reminder, if you phone in and we do one of your math problems on air, you will automatically receive a voucher good for a whole carload of people to go out to Holiday Lights at COM. We do have Matthew, a 5th grade student, in studio with us, and we are about to get you back to work. Are you ready, young man?
Yes.
All right, head on over to the board. Now, earlier you said that you're comfortable adding and subtracting fractions.
Yes.
So let's just make sure of that, all right?
Okay.
So I would like you to put up any fraction you want. So start over on the left-hand side of the board. So you can put, you know, like 3 over 5, 7 over 11, whatever fraction you want to come up with.
Oh,
2 over 4. So to that we're going to plus. So put an addition symbol in there. And now I would like you to put 5 over 10. So I'm not going to make it so easy where we had like denominators right away. So what I'd like you to do is explain to Devin how you would approach this problem. And if you get stuck a little somewhere, Devin is right there to help you out.
Now, I think the 2/4 was a really interesting choice for a fraction that you went with. Because it looks like it's equivalent to something else, but the values don't make it immediately obvious to somebody who's just getting into fractions. So tell us why you went with 2/4.
I didn't really know what the other one was gonna be, so I just picked this 2/4.
Now, is 2/4 really that random? Because what is 2/4 very similar to as a fraction? Well, let's think about it this way. What if we were to take a circle here, all right?
Okay.
Let's take a circle, and we split it into fourths, right? Because we know the bottom number of that fraction represents how many parts there are of the whole. And we represent 2 out of those 4 parts. Now, again, you know,
That's
my
half.
circles are yeah, that is 1/2, right?
Right.
So if we were to treat this half as 1 out of 2, yeah, this is 1/2. I'm going to go ahead and just kind of write that equivalent up there, 1/2. Now, 5/10 is also a very interesting fraction.
It's
Why
also
so?
1/2.
So you represent 5/10. If you had, let's say, a rectangle, I don't know if you got a chance to play around with these in kindergarten, but like a 10 frame perhaps, where it was broken up into 10 equal-sized pieces, and 5 of them are shaded in. Well, that's the same as if this top half is shaded in and you have 2 halves altogether. So yeah, 5/10 is 1/2. So when we say 2/4 plus 5/10, what are we really kind of saying?
1/2 plus 1/2.
What does 1/2 plus 1/2 equal?
1 whole.
Looks good to me, sir. What do you think?
Yeah.
Nicely done. All right, so now here's what I'd like you to do. Take the 10 and erase the 10. And make it an 8.
Aha. That changes things a little bit, doesn't it?
So erase the 1 because it's not going to equal 1 anymore.
Yeah, we can go ahead and get that out of the way.
There we go. Now you guys work on that.
So how might we use this same approach, this same line of thinking? We know that 5/8 is not going to be equivalent to 1/2, right?
Well, 4 is half of 8.
Oh, that's interesting. So if you're thinking about maybe breaking that up into 4/8 and 1/8, right?
Yeah.
Now, how does that relate to 2/4? If we think about this circle, we broke it into fourths. Could we break it into eighths as well?
Yeah.
So if we do that, how many of the 8 is colored in here?
Half of it.
So out of the 8, how many?
1/2.
Right. So like if I have 8, what is 1/2 of 8?
4/8.
4. So we can add all of these 8ths together, right?
Right.
So we have 4/8 plus 4/8 plus 1/8. How many 8ths do we have altogether?
9/8.
9/8. Is there another way we might be able to represent that maybe as a mixed number?
I believe so. Yeah.
How so?
We could do 1 and 1/8.
1 and 1/8, because 4/8 and 4/8 together, we kind of
Equals-
did that work already up here, a 1/2 and a 1/2. So that's 1, and then we have 1/8 left over that we bring to the side. 1 and 1/8. Man, we just broke that apart and put it right back together using just concepts of what equivalent fractions represent. That was really insightful, Matthew.
There
Nicely
you go.
done.
Yeah, I was going to say, I like the way that he's thinking about that and approaching fractions and taking them apart in a different way than what the book would say to do, you know, because I was like, oh, I'd automatically go turn that into 8s and things like that. But the way he's doing it works. And that's the key. Whatever way works for you and you understand it and you can apply it, that's perfect.
Hey,
So
the
nicely
book,
done
the
on
book
that.
don't taste that test for you, so nicely done, sir. That's your
Thank
mind.
you.
All right. Do remember we have phone tutors available until 5:30 this afternoon. First of all, before we go to our first phone caller, Kyle. Kyle, I believe, is a 6th grade student from Stockdale Elementary. We need you to call us back because we didn't get your phone number to call you back to put you on air with us. So Kyle, if you're viewing the program right now from Stockdale, call us back because we need your phone number. All right. In the meantime, we did have Samuel's phone number. And Samuel, how are you today? Hey, Samuel, are you there?
Yeah, sorry,
Okay.
I was muted.
Okay, so you're a 6th grade student at Hart Elementary, correct?
Yeah,
All
a
right.
GATE student.
Good.
Ooh.
All right, Matthew, a GATE student also. Samuel, as soon as you're ready, let's hear the math problem that you're working on.
Hello, Samuel.
Okay. Hi.
Hi.
All right, so explain it. Devin will write it down, and we'll go ahead and work it out for you.
Well, it says the formula for P equals 4 times S gives a perimeter P of a square with side length S.
So this sounds like, if it's okay, I'm going to jump right in here, if that's all right. How's it going? So it sounds like this is the formula for finding the distance around a square. You take one side and you multiply it by 4. So if we had, I'm going to go ahead and draw a square just right over here so we can visualize this.
Okay.
All right? So if we have a square and we don't know the length of the sides, we do know that if we add all the sides together, we're going
Then we'll
to get
the perimeter.
the perimeter, right. Now, instead of adding all that together, we can also just multiply whatever S is times 4, because this is repeated addition, right? We're adding S 4 times, we can just multiply it by 4. So if you know that fact, you can get there a little bit more quickly. So we know this formula. Is there anything more to the problem that you called in with?
Yeah, it says, how much greater is the perimeter of a square with a side length of 5.5 inches, or 5.5, than a square with a side length of 5 inches?
So we're comparing two different squares. One square has a side length of 5.5, and the other square has a side length of 5. So that's really interesting. And we're looking to make a comparison. How much bigger, right? So let's look at both of these squares, okay? Which one would you like to work with first, the 5.5 or the 5?
The 5.
Yeah, because that's going to be the quickest to figure out, right? Each of these is 5, so what would the perimeter be?
5 times 4 is 20, so 20.
Okay, so for our square with the side length of 5, the perimeter is going to be 20. What about for 5.5?
Hold on, give me a moment. This one I might need to take a while.
Well, let's think about it this way, right? We know, I'm going to go ahead and just kind of play around with this here. We know that each of these sides is 5 and a half, right?
Uh-huh.
So let's break each side down. Let's decompose it. Kind of like what Matthew did with his fractions, where he broke 5/8 into 4/8 and 1/8. Let's break 5 and a half to 5 and a half, or 5 and 0.5. So we have 5s and we have 0.5s. Let's go ahead and just add all those together. And we already kind of did most of this work, right? We know all these 5s together equal 20. So we have 4 halves, or 4.5s, right?
Which
If we
is-
combine all
yeah.
those together, what is that going to equal?
That's going to equal 2.
Brilliant.
You know.
So we have the 20 and the 2, which means our perimeter
Is
is going to
22.
be 22. Brilliant. So how much bigger is a square's perimeter if its side lengths are 5 and a half compared to just 5?
2 inches.
Yeah, 2 inches. So what's the relationship between the difference between the two? This times 4, because we have 4 more side lengths of that value.
Yeah.
That's wonderful, Samuel. I love the way you thought about that by breaking it down similar to Matthew. Nicely done, sir.
Very good. Thank you for that call, Samuel, and for phoning in today. You've got yourself a voucher good for holiday lights at
Those lights are
Com. So
everywhere.
nicely done. All right. Well, it looks like we've got Kyle on the phone right now. And Kyle, you're a 6th grade student from Stockdale. Is that correct?
Yes.
All right. As soon as you're ready, let's hear the math problem that you're working on.
A father left all his money to 3 children. Child A received 1/6 of the money, while child B received 1/7. Child C, who received the remainder, was given $23,490. How much money did child A receive?
Could you give me that total again for C? And first of all, I'm sorry for their loss. That, no child should ever have to go through that. But C made out pretty well here. So how much did C get again?
C got $23,490.
$490. That sounds like a night I had a couple of weeks ago on television. So let's think about this. What we're trying to figure out is how much did A and B walk away with, right?
Well, I don't think they even need to figure out both of them. Just one of them, I think. Is that correct?
Yeah, just A.
Just A.
Cut your work in half.
Well, I mean, halves are subjective here because we're dealing with some very particular fractions. So the first thing we have to think about, we know that A and B have a certain value. And I like to think about this kind of like a pie, like that circle graph that we worked with the fractions, right?
Mm-hmm.
So what we have to figure out is what fraction is C here. Well, that's going to require a little bit of play around, but not too much, right?
Yeah.
So if we think of this, we know that A plus B plus C together is going to equal 1 whole.
Mm-hmm.
So we got to figure out what A and B is together and figure out what the rest is for C. So if we add 1/6 plus 1/7, the easiest way that we're going to add these fractions is by finding a common denominator. With 6 and 7, they really don't have a lot in common. So it's sometimes easier to just multiply those to get a common denominator. It doesn't have to be the lowest common denominator. It just has to be something that's shared. So what number uses both 6 and 7 as factors? In other words, what do you get when you multiply 6 times 7?
6 times 7 is 42.
So we're working with 40 seconds. If we find equivalence, 1/6 is how many 40 seconds? Well, we know that to go from 6 to 42, we have to multiply by 7. Whatever we do to a denominator, we have to do to a numerator. So we multiply the numerator as well. That's going to be 7 40 seconds. And the same thing over here. How do we get from 7th to 40 seconds? Well, we multiplied by 6. And whatever we do to the denominator, we do to the numerator. We have to multiply that by 6 as well. So we have 7 40 seconds. We have 6 40 seconds. We add them together. We have 13 40 seconds. And we need to find out the rest of this pie of money for these kids whose names are only letters. And that's a whole other issue I got with this father. Anyway, let's talk a little bit about who's left here, right? 42 40 seconds. If we subtract that, we're going to get the rest of that share. 42 minus 13. Let's work with those numerators since we have a common denominator. If we subtract 42 minus 13, what does that equal?
29.
29. So we know that 29 40-seconds remain. This is a very bulky and unfriendly fraction because 29 and 42 do not have any common denominators. And we know that because 29 is a prime number. The only thing they got in common is 1. So we're not going to worry about simplifying or anything like that. But what's important about 29 40-seconds is that we know that 29 40-seconds is equal to this total. So we can use that information to figure out how much 1 40-second is. Because 29 40-seconds equals 23,490 over, well, something. We don't know, right?
Mm-hmm.
But what we do know is that if we divide this by 29, we're going to know what one of those pieces is worth. And that's going to be really helpful. So we're going to have to break out a calculator because time is a precious commodity in television.
Here you go.
Thank you very much. I was going to use mine.
Oh,
so,
whichever
got
one
it
you
there.
want. It's
But it's here. The tool is the key. 23,490 divided by 29. That's going to get us. Wait, did you have a calculator? You could have helped me out this whole time? Okay,
Yeah.
I appreciate you. Nice, Kyle. What'd you get there?
810.
So we know that 1 40-second equals 810. That's great. Now we're looking at child A. Let's call him Adam. Let's give him a name, right? Poor
Okay.
Adam has gone his whole life just being identified as just by a letter. We're going to give him an identity. Adam. Adam has 1/6 of the money that was received. We know that 1 40-second is 810. We know that 1/6 is 7 40-seconds. We know that Adam got 7 of these 40 seconds. We know that Adam got 7 of these 810s. So if we multiply, you know what? What am I saying we? If you multiply 7 times 810, that gives us a very meaningful answer here.
5,670.
$5,670. That is the share of what Adam was left in this ordeal.
There you go. Nicely done. Great problem. Thanks for phoning in. And for phoning in, you've got yourself a voucher to Holiday Lights at Com. So we hope you and your family enjoy that. We do have phone tutors available until 5:30. We'll be back with more right after this.
My brain needs a break.
Well, today we've got a couple of students from a variety of elementary schools in Bakersfield, and we're at the KCSOS building ready to work on coordinate planes, all right? So you guys have a geo board in front of you right now, okay? So how many of you have ever played Battleship? Have any of you ever played Battleship? Yeah, you guys, a lot of you have played Battleship, right? On the coordinate plane, there are 2 axes, the x-axis and the y-axis. Have any of you ever heard of those? Good, right? If we have an ordered pair of numbers, we always say the ordered pair x and then y, okay? So you can see that on these, you can move the x-axis up and down. So use both hands, right? Don't you just use one. Use both hands and use them on the sides. And make sure the x is horizontal, right? Just like this one. And just kind of see how it feels, right? You can move it around. And the same thing with the y-axis. All right, you should be able to move it pretty freely if you're using both hands. All right. What I'd like you to do is go ahead and put the axes in the center. So if we move the x-axis to the center, and you can count the number of pegs that would be above and below it. All right. There should be 7 below and 7 above. And then move the y-axis to the center also. And there should be 7 on both sides. All right. Then to make sure that it stays there and doesn't move, just take out one of the pegs and put it in the center. all right? That's called the origin, all right? If it was an ordered pair, it would be 0, 0, all right? Is everybody good so far? All right. So there are 4 quadrants. Has anybody ever seen the quadrants and what they're named and what they are? You have? All right, good. So what we're going to do is sometimes they think they go in clockwise, but they actually go counterclockwise. So this up here is quadrant 1, okay? All of the numbers that are in quadrant 1 are going to be positive, because if we're at 0, if the first number I say is 2, I'm going to go over 2, and if I go in a positive direction, I'll be going up. So this is quadrant 1. We're going to go counterclockwise. This is quadrant 2, quadrant 3, and then quadrant 4. When you guys get to junior high and high school and you see these numbered, they'll probably be numbered with Roman numerals also, okay? Just to give you a heads up on what's going to go on, all right? So you can also see that you've got a bag of rubber bands, so go ahead and open those up. And what I'd like you to do is I want you to, first of all, we're going to plot some points, all right? So the first one is going to be 0, 7. So as far as the x-axis goes, it's going to stay 0. And now am I going to go up or down 7? What do you guys think? If it's a positive 7, am I going to go up 7 or down 7? Up 7, right. So just count it. 1, 2, 3, 4, 5, 6, 7. So that point is 0, 7. All right? -4, 3. Go -4. So we're going to start -4. We're going to go 1, 2, 3, 4. So that's in the negative direction. And now 3. So we're going to go up or down? Well, +3, which way? Up. 1, 2, 3. All right? So remember, positive is always going to be going to the right and up. Negatives are going to go to the left and down. All right? Try another one. 5, 3. So +5, +3. Okay, so we're going to count over 1, 2, 3, 4, 5. And are we going to go up or down 3? Up. Good. 1, 2, 3. All right? So you guys getting the idea about this? Okay? So remember, ordered pairs will always be 2 numbers. The first number will always be the x-axis. The second number will always be the y-axis. Okay? So what we're going to do is plot a few more points with the students, and then we'll see if we can kind of make out a figure the next time with some of the 6th grade students here at KCSOS. And once again, a big thanks to all of those students that helped us out with that in the coordinate plane. Time now for today's museum moment. And in studio with us, returning from the Bakersfield Museum of Art, Melissa and John. Nice to have you guys back again.
Thank you so much. Thank you for having us.
I'm sure you had a nice holiday.
Oh, yeah.
Looking forward to the next bunch of holidays coming up too, right?
Definitely.
All right. So I appreciate everything that the Bakersfield Museum of Art has done with us so far this year. And are we ready to get into today's activity?
Yes, definitely.
All right.
So hello everyone, thank you so much for having us do the math. So just a little introduction about ourselves. My name is Melissa Banuelos and I am the Curatorial Assistant at the Bakersfield Museum of Art. What that means is that I help in selecting, organizing, and installing artwork in our permanent collection and in the traveling exhibitions that we host at the museum.
And I am John Olivo, also Curatorial Assistant, mainly focused on gallery prep and installation. as well as some writing and overview of like the content that we deal with and handle at the museum here and there, as well as event organization to some degree.
Yeah, and today we're going to be talking about pattern in math and art, featuring one of the pieces from our permanent collection. So what is a pattern, John?
A pattern is often a set of shapes or designs that are being repeated over and over again, and that often do not change. And if they do change, they are like very small details changing as it evolves. Also dealing with lines and numbers as well.
So where do we find patterns? Patterns can be found in nature or be man-made, meaning they can be something that we draw or create ourselves. So just in general, we'll have some examples about nature and man-made, and these are patterns can be seen everywhere around you. For example, my shirt has a pattern of stripes, and I'm sure that just while you're watching TV, you can see some patterns around your home. So we'll have some examples here for you. So here we have bicycles, but as John mentioned, when you start repeating this object, you start to create a pattern on its own. So this is something that could be found in your town or when you travel. Row of chairs, again, can be found in a classroom or really in a restaurant setting or really any building where you are. And we have some stripes. So this isn't a fabric that's twisted, but again, similar to my shirt, there is a repeating pattern of bars, which creates this repetition. And this is a close-up of a metal plate. So again, this can be found in buildings and on the streets.
I don't mean to interrupt you guys, but sometimes we do this in class where we'll take a close-up of something and have the students guess what it is. Right? So you get very close because they're sometimes so used to looking at something at a certain vantage point or a certain viewpoint.
Definitely.
Right.
And then take a close-up look at it and see if they can figure out what it is. Also something to show texture.
Yes.
Definitely.
One of the elements also. So sorry to interrupt you there. But
Oh, no
no
worries.
worries.
Wonderful.
And so often we also find patterns a lot of the times like on animals, nature, like things that are naturally from our world and that are growing and happening around us. And like even like ripples of water or even like canyons could have like repetitive lines or the rings inside of a tree. These are all patterns and things that are just always repeating itself.
Some more examples.
Some more examples. This one's a succulent that has such a beautiful spiral pattern going on. And then again, like I was saying, like the canyons could have many lines, waves, and shapes going through them that create awesome texture, pattern, and design. And of course, zebras being like one of the most iconic animals because of its black and white body patterns. And even then, it's like I believe like no zebra is truly identical, so it's like they all contain the same patterns, but even then there are variations based on their genetics. And then sand waves, just creating lines and rhythm.
Made by the elements.
Yeah, made by like the wind and like, you know, different things in the desert like the weather.
So now patterns in math. So we talk about patterns that we see every day in nature or man-made, but now, of course, we see patterns in formulas and in mathematics. So two types of patterns in math are sequence, based on addition or subtraction, and geometric, based on multiplication or division. So, you know, these can get vastly more complicated the more you study math and as you get older, but these are two of the most basic ones. So our first one here with 3, 13, 23, 33, we notice that each number is added by 10 to get the next one. So that is an example of sequence. And then in our second example, we see 1, 10, 1,000. So that's being multiplied by 10 every time. So that is an example of a geometric pattern.
And with this art that we call tessellation, it really derives from like these same ideas of pattern that we were talking about today. What's amazing about tessellations are like they're using so many lines and shapes, and often even creating illusions depending on how you look at them. Like with this example here, it's like if you look at the shapes as like some of them as a whole, it's like they're creating like these geometric illusions that play with our eyes. And with this one's a lot flatter, but it's kind of like looking at one of those things where there's like the gems within the
kaleidoscope.
Like a kaleidoscope, like just that kind of feeling, and like change and constant shapes like interacting with each other, like hexagons and different polygons that could like have multiple sides. So it's like with this one, like it can really be a lot of different shapes depending on how you look at them, or like how much detail you really want to observe.
Right, and then you could also get radial symmetry out of that also with the kaleidoscope and what you're talking about. But tessellations, I know, are a very fun activity for students to learn about, especially with patterns.
Yeah, definitely. And it really starts with simple shapes. For example, in our previous slide, you see just squares and just a couple of triangles. And then with that, you begin to add, and your pattern will get, it can be simple or it can get very complex and create those illusions that John mentioned. So patterns in art. You want to describe this?
Yes.
Oh, I'm sorry. I'll go back there.
And so we wanted to share this one because, like the tessellation activity that kids often go to, they end up kind of creating something familiar with the shapes they're cutting. And it's often using a square and cutting a piece out of the square and then taping it on the opposite end of the square to like kind of create like this little cube that you can really make a grid and pattern with. And like we do have a lesson on our YouTube that's really similar to this. So like there's definitely lessons available online to like explore more tessellation and pattern projects.
Right, and that is something pretty simple that a student can do,
Yes.
just a little piece of cardstock or something like that.
Exactly.
Draw a design of anything, cut it out like you said, and then just slide it to the top, the opposite side or whatever, tape it, and then just keep tracing it.
Yeah, definitely. Alrighty, so now we're going to be highlighting one work from our permanent collection that uses tessellations in a similar way. So this is the piece Metepec. It's a painting, oil on canvas, painted in 1995 by the artist named Alfredo Arreguin. So a little bit about Arreguin. He was born in 1935 in a small town named Morelia in Mexico. So he's a Mexican artist. And growing up, his grandfather actually really inspired him to become an artist. So his grandfather would provide him colored pencils and paints for him to start drawing. But then as a teenager, Arreguin moved to Seattle, where he has lived since the 1950s. So it was really there that he started to make artwork that incorporated his Mexican roots, which are really based on pre-Aztec culture and spiritualism, as well as his life in the Northwest, which if you ever have been to the Northwest, it's very lush, it's very green. So he uses these two influences to create work that kind of feels like it's hovering between real world and fantasy. It's very mystical, and with this example, he uses tiny masks as part of his tessellation. So we can go to the next slide and see that in detail. So as you can see, there are hundreds of tiny, tiny masks here. Like a tessellation, they fit all next to each other. He uses a diamond shape. And each one is so different. Even though his works are quite large, this one measures 4 feet by 4 feet, he uses a very tiny brush to create these works. So, of course, he'll start with one, and then as he begins to group them together, and thus creating a tessellation. So this particular painting has between 300 and 350 masks because there are other details that kind of look like otherworldly creatures. So it looks like he's pulling elements from this fantasy land, something that he creates, from his mind, but that is still very influenced by his upbringing and his life in the Northwest. So as we can see here, just as an example, this mask here, this mask alone, it's got some green, it's got some purple, it also has got some tan and black to give this mask its features. So again, this is inspired by his Mexican roots and where he lives now in Seattle. So if you do look up more of his work, a lot of it is similar in the way that it plays with patterns, but they are each so vibrant and mesmerizing. So again, the artist is Alfredo Arreguin. So if you are interested in seeing more of his work, definitely you can Google him or visit his website, and his paintings are really, really beautiful.
There you go, and certainly is impressive, which is why I wanted to go back again, and that way they can see the student or the artist's name up there. And once again, both of you, thank you for coming in again and showing us how patterns in art and math work together right there. Nicely done.
So
That is today's museum moment. We'll be back with Matthew right after this.
Hi everyone, Willow here from Camp Keep. Have you ever noticed that your shadow changes length throughout the day? And it also seems to change direction. Now I'm 63 inches tall, 5'3". It's about 7:30 in the morning in this video, and look at how long my shadow is. It's almost twice as long as I am tall. What's that all about anyway?
Well, I've got a little experiment for us.
Me closer than pages that stick in a book. We're closer than ripples shadow in a brook. Wherever you'll find him, you'll find me. Just look closer than a miser or the bloodhound's Eliza me.
Well, to start this shadow experiment, let's talk about shadows themselves. What is a shadow? There's a shadow right there, hanging out in the corner of the screen. Why is there a shadow there? Well, if you're going to talk about shadows, the first thing you have to talk about is light. Now, you have to have light in order to create a shadow. Now, here's the cool thing about light. You shine a light, boom, and the light just radiates out. Now, we can't see a beam of light, but we can see the result of it, and that light can get really bright on the wall. It's even creating a halo kind of reflection, and it bounces off whatever object it's hitting. So what happens if something gets in the way of that light? Well, light is blocked from its destination, and now you've got a shadow.
You know, Kat, I'm not sure. So let's collect some more data. I got this bottle. It's 9 inches long, and I decided to put it out in the street in the same spot every hour. And I got about 11 hours. I took a picture, and I measured the length of the shadow. How does that shadow change? What do you notice? Is there anything that stands out to you that's interesting? Do you recognize any patterns? Why does the shadow change? So I noticed that it was in the early morning and the late afternoon, evening that the shadows got longest. And I also noticed that their angle kept on changing. So I decided it was time to play with light. So what happens if the light source is far away from the object? Or what if it gets really close to the object? How does the shadow change? What if the object gets closer to the light source? What happens to the shadow? So it seems to be getting bigger and smaller, but I'm not seeing the angle change. So then I decided, what if the light source changed direction? It's way up in the sky. The shadow is low. And now, as the light source changes, the angle of my shadow changes.
All right, so who cares? So what? What does all of this mean? Well, let's take a look at all of our clues. This is my list of observations and some clues. And I noticed first, okay, objects block light, and that's what makes a shadow. Then I noticed that the shadows, they seem to be longest during sunrise in the early morning and sunset. That was a pretty consistent pattern, which was pretty interesting. Now, you got to have a light source. I'm thinking the light source is the sun, right? It's outside, and we also noticed that if the object or the light source moves around, then the shadow changes. Okay, so a moving object or light source, well, the object didn't move, but the sun moves. It moves through the sky, and it's moves starting sunrise all the way across the sky to sunset. So if the sun is crossing through the sky and we have our object right here all the time, if the sun is here, the light is going to be shining this way and the shadow is going to come out over here. And if the sun is right here, the light is coming straight down and you're not going to get much of a shadow. If the sun is over here, the light's coming straight down and whoosh, there's your shadow. And so these early hours or these late hours of sunrise and sunset, you've got the longest line, the longest angle of the sun hitting the object. And so you get these long shadows. Again, a long angle, boom, hitting the object, long shadow. So we figured it out. It's the sun moving across the sky from east to west that causes shadows to change. Sometimes they're longer, sometimes they're shorter, and their angle changes as the sun changes going across the sky. I hope you had loads of fun doing this shadow experiment with me, and I hope you keep playing with shadows.
All right, a lot about shadows right there. Also, thank you to our friends from the Bakersfield Museum of Art. In studio, we have Matthew, a 5th grade student from Stockdale Elementary with us. He's been working on adding some fractions. We're going to work on multiplying them in just a moment. But before we do that, because you've done some great work so far today, I would like to award you with a meal from our friends at Broken Yolk. So congratulations on that. Hopefully you have an opportunity to go enjoy that. So, you ready to multiply fractions now?
Yeah.
All right, over to the board, young man. Once again, I will let you have the first fraction. You may put up any fraction you like, and then I'll come up with the second one.
I don't know.
It's up to you. It doesn't have to know. It can be anything random.
How old are you?
10.
Okay, and you're in 5th grade?
Yeah.
So put 5 over 10.
All right.
And then instead of addition, we're going to multiply. So put a multiplication symbol next to it. Draw your fraction bar. And Devin, how about you come up with the second fraction this time?
Do I have to do my age?
No, we're not going to do our ages.
It's the 12th month, so let's go with a denominator of 12.
Okay.
And tomorrow's the 2nd, so let's do 2. All right, now, just out, have you started multiplying fractions yet in class?
Kinda.
Kind of. What is your, before you solve this, tell me how you think you might solve this.
Kinda simplify the fractions, then multiply the numerators.
So go ahead and you want to simplify those first. Put them into simpler terms. Okay, let's find an equivalent that's easier to work with? Which one would you like to work with first? 5/10 or 2/12?
Well, 5/10 is a little easier because it's 1/2.
If you joined us earlier in the program, yeah, we already put that work in, so there's no need to do it all over again. Go ahead and rewrite 5/10 somewhere else off to the side as 1/2. Okay, now what about 2/12? Could we simplify that as a fraction?
We could break it up.
We could decompose it, but we want to keep the value of that 2/12. So how else could we represent 2/12?
1/6.
1/6, great. You saw that 2 and 12 have a common denominator of 2. All right, we have 1/2 and 1/6. How might we multiply these fractions?
Well, we could decompose 1/2 because you can't really decompose 1/6 anymore.
You're thinking back to addition, and I love that connection you're trying to make with addition and subtraction. So you're trying to decompose. And that's based off of the visual. Let me recommend something as far as the visual.
Okay.
All right? I'm going to have to refresh my
You guys will have
here.
about 2 minutes left.
Let's draw a square. Because if we do multiplication with area, we multiply one side by another, right?
Right.
But let's say that instead of the whole square, we use some crossovers here, right? Let's say that one side here is 1/2. And this side is, let's say we only want to fill in 1/2 of the area of this going this way, right?
Right.
I'm going to go ahead and just cross some lines over here, right? Okay, so what I'm crossing over is 1/2. So 1/2 go in this direction. Now I want to do the same thing. I'm going to do it in 1/6, right?
Right.
So I'm going to split this square into 1/6 and shade only one of these 1/6 in, okay? I'll do this one here. See how I'm going in different directions? You can do this with highlighters on paper with different colors, and you can see, like if you have blue and yellow, there's going to be a part that's green because blue and yellow mix. If you do it with red and yellow, one is going to be orange, red and blue, one is going to be purple. But the idea is, how many of these sections have both green and red?
6 of these.
Well, let's see. I think just this one has green lines and red lines in both, right?
Right.
So that's just one. Now, how many rectangles did we split this square into in total?
6.
Well, we have 6 up top here. What about down here too?
We split them all into 12.
So we have 12, right? So that means only 1 out of 12 of these pieces is shaded in both colors, which means that 1/2 times 1/6 is 1/12. Now, what do you notice about 1/12 and multiplication going across here?
You kind of 1 times 1, 1, 2 times 6, 12.
Absolutely. In fact, that's a nice way to quickly do multiplication of fractions. You can multiply the numerators and then multiply the denominators, and that's where you end up.
Nicely done, guys. 1/12. Perfect work right there. So, Matthew, I've got 2 questions for you. Did you learn a little something today?
Yeah.
Good. I'm glad you worked well with the fractions. I was very impressed with how you approached those and came up with those.
Thank you.
Did you have fun?
Yes.
Even better right there. And do remember, we have phone tutors available until 5:30 this afternoon and every Tuesday and Wednesday throughout most of the school year. And until we meet again, continue to do the math.
Major support for Do the Math has been provided by CHEVRON, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary STROOPE Family Foundation, Panama-Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.